Okay, the first question has four diagrams and it shows two forces in two of the diagrams and three forces in two of the diagrams. And we are supposed to calculate the net force. Okay, the diagram is a little tricky. You need to understand that this solid patch, it's a surface like this page, and its orientation is like this. And the arrows going up actually are perpendicular to the surface, and arrows going left and right, they are parallel to the surface. Since it's a three-dimensional diagram, so it's hard to visualize it sometimes on the board, so you can visualize it like this. So the arrows, they are which are perpendicular, they are going up, and all the other arrows, they lie into this surface. Which, when I say they lie into this surface, it means that it can be directed anywhere in this two-dimensional plane. So if I try to plot it here, so this is our first problem. So we have a surface of this kind, any random surface, but imagine it like a page and it's oriented like this. Okay. So any force or any arrow which is shown as going upward, this is perpendicular to this page. It's like on top of this page, going upward. The other arrows, they goes in plane of the page. So for example, the second arrow, which seems to be coming this way, this arrow is actually lying on the surface, coming out like this. Okay, so that's the way how you visualize this problem. So this is your surface. This arrow is perpendicular going upward, and this arrow is coming out of this surface. And so you are supposed to find the resultant of these two forces or these two vectors in general. So in last video, last lecture, I told you about how you add two vectors. That was a head to tail rule. Like you take one vector and you put its tail on the head of other vector. So we can take this vector, put its tail at the head of this vector, and then we can add them. Or we can take this vector, put its tail at the head of this one, and then we can add them. Both should give us the same result. So I'm gonna take this first vector. Let's call this first vector A. Let's call this vector B. Although they did not name them here, but it's fine. You can just give them any name. So if I take this vector now A and put it here such that I do not change its direction and its magnitude, which means its length should stay same, and its direction, which is represented by this arrow, it should stay same, then I get this one. And their resultant should be the vector which joins the tail of first vector. In this case, the first vector is vector B, and the head of second vector, which is in this case this blue vector. So this vector, this line should be their resultant. So this is their resultant, and this is equal to vector A plus vector B. Okay, so now you see it seems like that this is in the planes, but this resultant is not in the plane. So what's going on? What I did this thing. So this was my first vector, this blue pointer, and this black was my second vector. Okay, so I take blue here and I place it at the top at the head of this first vector. So this vector red, which joins the tail of both of these, this is my resultant. So this is still up in the air. This red vector is still, it's like this one. Okay, let me actually put them here. So this is my first vector. This is my second vector. And their resultant is something like this. So it's hard to draw in plane of the board, but you can visualize it. Even better visualization is like if you put this vector here, and the black one was the one which is perpendicular to the surface. Blue one is this one. Now you use head to tail rule. How you do that? You take the first vector, you place its tail at the head of second vector. This was my origin where this first vector lies, and then I coincide them like this, and this red pointer here is the resultant. So you see it's in reality it's something like this. That is a little confusing, but when you think about it, you start visualizing these things. The second one, it's easy. It's everything is lying in this plane. So I'm again gonna mark the surface something like this, but consider it as this page. So this is our surface. And now we have three vectors. Let me give them different colors. We have, let's say this is the origin of our coordinate system. Let me use black for this one. So this is x-axis, this is y-axis, and we have three vectors. The first vector starts here, goes in this direction up to this point. The second vector, it goes in the opposite direction here. It's a bigger one, and it's this one. Let's call this vector B, call this one vector A, and then we have a third vector. Let me use a different color for that, and that is this vector. I'm showing it a little down from this point because I do not want to just paint it on top of that color. So this is my third vector. Let's call it vector C. Okay, and if you try to visualize it on this plane, then it's this plane, and these vectors are lying somewhat like this. So blue is towards left, and green and this color, whatever it is, they are towards right. Okay, although my these markers, they are of same length, but these vectors, they are not of same length, and so when you add them, they will give you some non-zero resultant force or resultant vector. Okay, so that's the situation, which is if you try to draw it on board, looks like this. So again, the same rule you take, and they are in opposite direction, so it's easy to add them. What you do, you take first vector, add it to the head of vector, second vector. So I'm gonna take this red vector, and when I add it to the head of this vector, so it will be somewhat like this. You see, I did not change its length, I did not change its direction, I just take this entire vector and added it to the B. Now I'm gonna take this vector C and do the same thing. I'm gonna add, since this is my third vector, it goes at the head of second vector. So I'm gonna add green one here. Okay, so this is my vector C. And now you see they end up in this diagram, they end up of same length. Like the length of blue vector is equal to the sum of length of this color and this green one. And so in this case, you can say that maybe resultant is 0. It can be non-zero, maybe my drawing is not precise, but in any way, so my resultant would be, let me use red. So the resultant will be, it starts from here, it ends at the head of this green vector. Okay, in this diagram, it seems like they are just equal, and so the resultant vector is 0. But let's say in general, if they are not 0, let me decrease its length a little. So let this be vector C. Let this be vector C. Okay. So in this case, you see, this will be my resultant vector. This small red vector is resultant vector, and it's directed towards the direction of blue vector. Or if you want to name in terms of coordinate system, so all the vectors which are pointed towards positive x-axis, they are positive. So in this regard, if you want to write a vector equation, A is positive, C is positive, blue is towards negative x-axis, so blue is negative. So when you add them, their sum R will be A positive, B positive, and C negative. And now you see it purely like the sign of resultant vector, whether it will be positive or negative, it purely depends upon this sum. If vector C is longer than the sum of vector A and vector B, your resultant will be negative. Otherwise, it will be positive. So that's how you do that. And again, this diagram was easy, but this kind of diagrams, you have to be careful about them. So these things, like when you try to draw them on page or on boards, they are hard to visualize. The best way is to just stare at the diagrams and think about them. That's how you get the visualization, like how the resultant is turning out to be. Okay, I'm gonna skip the third one. It's just like this. It's just that the vector goes in this direction, and so I'm gonna do the last diagram, the fourth one. And the fourth one is little tricky, so let me try. Again, I have page like this. This is my surface, which is the black surface in the questionnaire that you have. So it's like this. Then I have a coordinate system. This is my x-axis. Let's call this y-axis, and z-axis is this one. Can you perceive where this z-axis is? If I try to put this sheet here, where is this z-axis? So you can see x will be along this direction, y will be a perpendicular one like this black marker. Where would be the z? Z is actually coming out of the plane of the board. So it's like if I put a page here, sorry, I'm not sure if you guys can see it or not. Then this black is x, this green is y, and this color is z. So this is what this diagram represents. Okay, so they all are perpendicular to each other. Okay, now this is precisely how these vectors actually are. So let me use blue for vector A. So first vector is along y-axis. So let's say this blue is vector A. Then the other vector, it's somewhat in this direction. Let's call it vector B. And then the third one, it's in this direction. Let's say this direction. This is my vector C. Okay. So there are two ways to add them. The first way is the one that I used here. Like you just take vectors, you do not change their magnitude, you do not change their direction, and you add them. I'm gonna do that one first, and then I'm gonna explain the other one. So in this case, if I take this blue one and this one, which color is it? Magenta? Not good with colors. Okay, let's call it red. So blue, I am gonna take blue one and this one and add them to vector B. Okay, so I'm gonna take blue first. So I take this vector, put it here. Seems okay, same length, same direction, I just add it to vector B. And then I'm gonna take this one and add it here. Okay, so this is my vector C. What's the resultant? Resultant will be this vector, which starts from origin here and goes up to the head of this final one. That's my resultant vector. It's very confusing, so let's try to understand them again with these markers. So this is B. Let me use the sheet of paper. Let's use this one. This is my x-axis. How can I do it where anyone can see it? Okay, so this line that I have drawn on paper, this is this line, this x-axis. I'm gonna put it here, like this. And on this line, you can see that vector A is perpendicular to this line. So this is your vector A. Vector B, which is green one, it's in this direction. And vector C, this one, it's in this direction. Okay, so now you are supposed to take this blue and this magenta vector and add them to green vector. So I take this one, put it here, and then I take this one, put it here. So my resultant in this case is gonna be this vector. So this is what this diagram represents. Okay, so it's better when you take your pens and try to put them on table and point them like what they gave me. The second way is easier. Second way, you resolve a vector into its components. We also talk about it in our last class. And how do we do that? Now you don't do that. You don't have angle. So that's the way you add vectors. So I'm not going to do the other way. Do you have questions? It's confusing, I know, but it's better if you try with your pens. You understand them better. I tried my best, but I'm not sure if you guys are okay with that or not. Question 2. In question 2, you are supposed to draw the force diagrams. These diagrams are also called free body diagrams. In a free body diagram, you represent an extended object with one point. What do I mean by an extended object? An object like ourselves. For example, if I'm running on the ground, okay, and you try to draw a picture of me running on the ground. So you do not try to draw like entire body of me. You just mark a point there. Okay, you're like, okay, this is Fussy and it's running in this direction. That's it. That's how you represent objects in this class. And these kind of diagrams, they are called free body diagrams. So you just put a point in place of an entire object. So that's me. When you draw a free body diagram, that's me. And then what you do, you represent all the forces acting on it. For example, I have my weight acting in downward direction. We all have weight and it acts in downward direction. And then the ground exerts a force on us. That's called normal force. So normal force will be in the upward direction. There is friction between ground and my feet. So frictional force will act in the backward direction. That's it. So such kind of diagrams you are asked to draw in this second problem. So you have different objects and you are supposed to draw such kind of diagrams. So the first one is a heavy crate is being lowered straight down at a constant speed by a steel cable. So the object is crate. So what you do, so this is first part. So this is crate. It just looks like me as I try to draw myself in free body diagram. So this is crate and it has weight in the downward direction. All objects have weight. But they say that it's been lowered at a constant speed by a steel cable. So there's cable attached on the other side. So this is cable. And there's a force which cable is exerting on this crate. This force is called tension. It's similar to normal force, but if you are using a string or a rope or a cable to move an object, then the force is called tension force. And it's being lowered at a constant speed. Constant speed tells you acceleration is zero. That's perfect. So that's the main point of this question. It's been lowered at a constant speed, which means there is no acceleration on this system. If there's no acceleration in this system, it means there is no net force in this system. So I'm going to try to write it in mathematics. So Newton's second law tells us that sum of all the forces acting on the object equals mass of the object times acceleration produced in the object. But since this system is being lowered at a constant speed, there is no acceleration in it. So right hand side becomes 0. Okay. Now this right hand side demands that this sum of forces, which is the left hand side of the equation, this should give us 0, because right hand side is 0 and equality demands that if right hand side is 0, left hand side should be 0. Okay. So now what are the forces in the system? We have weight and we have tension force. And then you choose your coordinate system. Let's say positive y-axis is upward, positive x-axis is towards right. We see that this object, this crate or whatever it is, it moves upward or downward. It doesn't move sideways, which means there's no motion along x-axis. And if I write an equation for x and y-axis, this becomes summation fx equals max and summation fy equals may. This equation is satisfied because there is no motion along x-axis. This crate doesn't move left or right. So if it doesn't move, acceleration is 0 and force is 0 because there's no motion. So the only equation that we are going to use is this equation. And so if the system has zero acceleration, it means it has a y equals 0. So this equation gives you this equation. And now for the forces, tension force is towards the positive y-axis. So this force is positive. So we take T to be positive. And weight is in the downward direction. That's negative y. So it should be negative. And so this is our resultant equation. This tells you that tension is equal to weight. This equation. That's what it means to be lowered at constant speed. If we just let it go, it's gonna accelerate downward. So the entire purpose of this cable is to lower this crate at a constant speed so that it doesn't fall down and doesn't break. Okay, a second one, a boy is pushing a box across the floor at a steadily increasing speed. Let the box be the system for analysis. So this was a vertical motion. In this case, we have a floor and we have a box on it. So this is box. It always becomes a point when you try to plot a free body diagram. So this was crate, this is box, and a boy is pushing on it. Let's say the boy pushes it towards right. So the boy is applying a force towards right, and let's represent that force with F. There is a weight of the block, this block, W, and then there's a normal force from the ground, which is in the upward direction. And what else is there? Speed is increasing. Okay, it says it's at steadily increasing speed, which means there is acceleration in the system. Okay, now you can, there's no other information in the problem. If you want, you can assume that there's a frictional force between this block and the ground. So it's always there, so there can be frictional force. That's represented by small f. And that's it, that's all the forces. But we know that there is acceleration in the system. So that this one is moving in this direction, and so along x-axis, which is not equal to 0. So acceleration is not equal to 0. Again, we are going to use these two equations. The first one, summation f x equals max, tells us that since acceleration is not 0, right hand side is not 0. So, and left hand side, F, the force that the boy is exerting, it's positive because it goes towards positive x-axis, this convention. And this frictional force, it is negative. So under the action of these two forces, the object is moving towards right, which means that the force that boy is exerting is greater than frictional force. And as time goes by, the boy is pushing it harder and harder so that its speed is increasing. That's what it means. Now for the y-axis, summation Fy equals 0. Okay, it's equals MAY, but you see this box or block or whatever it is, it just moves on the x-axis. On the floor, it doesn't go up or down, which simply means that there's this net acceleration is 0 because there's no motion along that. And so left hand side should be 0. So normal force is acting upward, weight is acting downward, and so normal force should be equal to weight. So there's no net motion along the y-axis, but there is a net motion along x-axis, and this equation tells us that. Okay. Third one is important. Let's do it for this one, and this is a bicycle speeding up down the hill. So we have a bicycle. So let this be the ground, and this is the hill, and let this be the bicycle. Okay, and problem says that the bicycle is speeding up as it goes down the slope or down the hill. And friction is negligible, so we don't need frictional force, that small f that I plotted here. So here's the thing, let this be the angle theta, the slope of this plane on which the bicycle is coming down. So we have weight of this bicycle coming downward. Okay, but you see this weight, it's not along this plane. And what I'm doing, I'm choosing my coordinate system like this. This is positive y, this is positive x. Look at the choice. I had made this choice so that my problem becomes easy. First, it's not the same as this choice. It's tilted. It's like I have moved it like this, and so it becomes like this, so that I could align it with this plane. Secondly, in that one, I have my positive x-axis towards right. Here, I have my positive x-axis towards left. Can anyone figure this out? Why did I do that? Why I chose my positive x towards right in that diagram, and here I chose it to be on the left? Why? It's just the way I have drawn these diagrams. Here I assume that the crate and the block, they were moving towards right, and so I chose positive x-axis in the direction so that I could get positive acceleration. Here I have drawn my diagram such that the bicycle is coming down this way towards left, and so I have just redefined my x-axis positive towards left. It does not affect your final result. You could have equally well made this diagram like this. This is angle theta, this is bicycle, and it's moving this way, and in this case this would be my positive y, this would be my positive x, and these both should give you the same answer. Okay, so this choice is purely yours. There's no hesitation in that. So let's go with this one. So this weight, it's not along x or y axis, it's in this direction. So what we do, I resolve it into components. This is one component, this is the other component, and now if you look at these two blue lines, this blue line is towards negative y-axis, this blue line is towards positive x-axis. So this angle is theta, same as this one. So this side becomes w cosine theta, and this side becomes w sine theta. There should be normal force from the surface. So the normal force is in this direction. And now that's all the forces acting on the system, and now we are going to use these two equations. So let's look for x-axis. Summation fx equals max. So we need to, since bicycle is speeding up, it's been told in the problem. So we have a non-zero acceleration, so we should have a non-zero force on the left. And if you look at this diagram, this w sine theta, it's along positive x-axis. So w sine theta is positive. Okay, and there is no other force which is acting in the opposite direction of w sine theta. And so this is equal to max. So the entire acceleration is being produced by the weight because it's coming down. And similarly, when you apply summation fy equals 0, not 0, sorry, it's may, but then you see that the bicycle is not going up the ramp. It's just moving in a line. So it's not moving upward or downward, and so you conclude that ay is 0. And if ay is 0, on the left side we should have 0, and we immediately see that normal force, it's along positive y-axis, so normal force minus this component of weight, which is w cosine theta, this gives us 0. So you see this is different. In that case we had normal force minus entire weight equals 0, but in this case it's not entire weight, it's some component of weight which is balancing normal force. I have 1 more minute, and this is one interesting fourth problem. Just think about it, what it says. It says that you are in the middle of a frozen lake. There is zero friction, there is 100% friction, which means you cannot walk. And the only thing you have with you is a bunch of stones. And you want to get to the shore. How you are going to do that? And it also put a restriction that you cannot put the stones on the floor and walk on them, because the friction is also 0 between stones and that frozen lake, and so you cannot walk. So how are you going to do that? How are you going to get to shore? You cannot walk. What do you think? How can you get to the shore? Remember Newton's third law? It says if you apply a force on an object, that object is going to apply a force on you in the opposite direction. So what you do, you start throwing stones in one direction. You throw a stone, the reaction force act on you and you move in the backward direction. So if this side is the shore and you have a lot of stones and you start throwing stones in this direction, you will eventually get to the shore by simply sliding on the frozen lake. That's allowed by Newton's third law, and it happens actually. It happens more visibly if you see in movie or on TV that if you try to fire a gun, not like revolver or pistol, but a bigger gun, they try to hold it against shoulder. Why? Because the gun exerts force on you, and the shoulder gives you, it stops you not moving backward. So that is like a sport. That's why they always hold guns like this. Sorry, it was a bad example. I shouldn't be talking about guns, but that's like the best example I could come up with.